Welcome back. If you're studying for your Cambridge Computer Science exams, whether that's syllabus 0478, 0417, 2210, or 9618, you've probably realized by now that some topics literally make or break your final grade. Today, we're targeting one of those high-value, high-mark topics, logic gates and circuits. We are going completely under the hood of your favorite devices to see exactly how computers use simple ones and zeros to make the complex, real-world decisions that power our modern lives. I see two types of students tackle these questions in past papers. You've got students like Alex who overloads their answers with raw computer science facts but provides absolutely zero analysis, and then you have students like Sam who rushes, completely misses the command word requirements, and throws away easy marks. Today we're fixing both of those approaches. We're going to treat this explanation like a strategic workout, maximum effort in short bursts so you can tackle those high-mark questions with explosive power. Let's decode this invisible architecture together right now.
Here is our mental roadmap for today's session. We'll start at the absolute ground level with the Boolean foundation. Then we'll meet the three basic gates. From there, we'll upgrade to advanced logic gates, learn exactly how to stitch them together into combining gates into circuits, and finally, look at real-world logic systems so you can crush those scenario-based exam questions.
Section 1, the Boolean foundation. Okay, let's dive into the absolute simplest concept underlying all digital circuits, because before we can build a perfect exam answer, we need to understand the basic materials. Our primary building materials are logic gates. Now, if you get a question asking you to define a logic gate, do not just waffle. Use the exact terminology the examiners are looking for. You can think of these gates as the tiny, invisible decision makers inside a computer chip. By definition, they are the basic units of a digital circuit, and their sole job, their absolute primary function, is to control the flow of electronic signals. But remember, computers don't speak English, or Spanish, or Mandarin. They don't understand nuance. They speak purely in binary data using what we call Boolean operations. When you see the word Boolean, I want your brain to instantly lock on to the idea of a binary choice. It's an either-or scenario. There is no gray area here, and understanding that strict binary nature is your first step to securing top marks. Take a really close look at this table. Notice exactly how normal human language translates into a computer's binary language here. This is crucial for word problems on the exam. All the complex data entering these logic gates is boiled down to two incredibly simple states. First, we have the Boolean value true, which the computer fundamentally sees as a binary 1. Depending on the scenario the examiner gives you, you might also need to think of this one as on, yes, or positive. Then, on the flip side, we have false, which translates to a binary 0. In a real-world scenario question, a 0 means off, no, or negative. That's literally it. Every single piece of software you use, every complex video game you play, every automated digital system you interact with daily fundamentally relies on just these two microscopic states interacting millions of times a second. Before we move on to the actual gates that process these states, I need you to commit this table to memory. It's the absolute bedrock of everything we're about to do.
So now that we've mastered our ones and zeros, let's transition into Section 2. The three basic gates. These are the fundamental pillars that actually take those Boolean values and do something useful with them.
Now, what's really interesting and absolutely critical for your exam is how visually distinct these fundamental logic gates are. Examiners will ask you to draw these, and they are incredibly strict about the shapes. If you draw a sloppy gate, you lose the mark, period. So let's look at them. On the top, you have the NOT gate. It's distinctly shaped like a triangle, but pay close attention to that tiny little circle at the tip. That circle is actually the most important part of the symbol, representing inversion. We'll talk more about that later. In the middle, we have the AND gate. Notice how it's perfectly flat and straight on the input side and smoothly rounded on the output side. It literally looks like a capital letter D. Think AND ends with D, and the gate looks like a D. Finally, at the bottom, we have the OR gate. This one has a curved, swept-back input side and comes to a sharp, distinct point at the output. These specific shapes are the universal language engineers use to map out circuits, and they need to be second nature to you. Let's look at the AND gate in action using something called a truth table. In your exams, you will be asked to fill these out constantly. A truth table maps out every single possible combination of inputs to prove what the final output will be. For an AND gate, it takes two inputs, which we typically label A and B. Now look closely at the output column labeled X. The output is only a 1, meaning true or on, when both input A and input B are exactly 1. If you look at the first three rows, if even a single input is a 0, the output is ruthlessly shut down to a 0. It is a highly strict gate. You absolutely must have both conditions met to proceed. Before we continue dissecting the rest of these truth tables, subscribe to our YouTube channel Ace the Exams at acetheexams_IGCSE to excel in your Cambridge examinations. Click that subscribe button and hit the bell icon right now. Okay, let's jump back in and look at the OR gate, which operates with a completely different mindset.
Now, we need to clarify a massive point of confusion that trips up students like Alex and Sam all the time. There are actually two distinct types of OR gates, and you need to know the difference. The standard OR gate, the one we just looked at the shape for, is what we call inclusive. That means the output turns on, becoming a 1 if input A is true, if input B is true, or if both are true. Think of a security light outside your house that turns on if it detects motion, or if it gets dark outside, or if it's both dark and there's motion. It's highly flexible. But then we have the exclusive OR gate, which you'll see written as XOR. This is the tricky one. This gate comes on only if A is true or B is true, but absolutely not both. It literally excludes the scenario where both inputs are 1. If you get an XOR gate on a past paper, highlight that X immediately so you don't fall into the inclusive trap.
All right, with our primary pillars firmly in place, let's level up and move into Section 3, Advanced Logic Gates. This is where we start seeing the questions that really separate the top-tier grades from the average ones.
I want you to pause and think about this logically before I just give you the answer. In computer science, we don't just memorize, we analyze. What exactly do you think happens when we take the strict rules of an AND gate or the flexible rules of an OR gate and we forcibly push their final output through a NOT gate? Remember from our first slide, a NOT gate acts as an inverter. It violently flips the reality of the signal, turning 1s to 0s and 0s to 1s. So what kind of monster gates does that create?
Enter the Revel gates, the NAND and NOR gates. Let's analyze their visual symbols first, because examiners love testing you on this. Notice that these symbols look almost exactly identical to the basic AND and OR gates we studied earlier. But there's one absolutely crucial, tiny difference. Look at the very tip of the output. There is a small, hollow circle. In diagram logic, that little circle is the shorthand symbol for a NOT gate. It means the standard output of the gate is being completely inverted or flipped at the very last microsecond before it leaves the gate. Missing that little circle when you draw your diagrams will cost you the entire mark for that question. It changes the entire meaning of the circuit. Let's break down the exact unbreakable rules for these advanced gates. If you're taking notes, this is the slide to screenshot. A NAND gate, which stands for NOT AND, is literally an AND gate fused with a NOT gate. Because a normal AND gate only ever outputs a 1 when both inputs are 1, the NAND gate does the exact opposite. Its output drops to 0 only when both inputs are 1. In every other scenario, it pumps out a 1. Next, the NOR gate acts as an OR gate plus a NOT gate. A normal OR gate outputs a 1 almost all the time. So, a NOR gate is incredibly restrictive. It only outputs a 1 if both inputs are absolute zeros. And finally, just to recap our tricky friend from earlier, the XOR, or exclusive OR gate, outputs a 1 exclusively when the two inputs are completely different from each other, like a 1 and a 0 or a 0 and a 1. Stop scrolling. Subscribe to our YouTube channel, Ace the Exams at acetheexams_IGCSE to excel in your Cambridge examinations. We've helped thousands of students improve by 2-3 grade boundaries. Join them right now by subscribing to @theexams_IGCSE and turn on all notifications so you never miss our weekly exam strategy sessions. Let's keep this momentum going and move into Section 4, combining gates into circuits. This is where we transition from looking at individual isolated gates to analyzing actual working logic circuits that perform complex real-world tasks. This is the heart of Paper 2.
When you turn the page of your exam booklet and you first look at a complex logic circuit diagram with lines crossing everywhere, it can trigger instant panic. It looks totally overwhelming, but top students have a system. The secret to demystifying these diagrams is to break them down methodically, step by step. First, you never look at the whole thing at once. You locate the intermediate outputs. These are the checkpoints where the first set of gates finish their specific jobs. Second, write down the Boolean expression or the truth table values for just that first isolated part. Ignore the rest of the circuit entirely. Finally, once you have that intermediate result securely figured out, you take it and trace it into the next gate to find your final output. Let me show you exactly how this looks in practice.
Let's do a quick visual workshop right here. Look at this combined circuit. Instead of panicking at the whole image, focus purely on the dotted box. Part 1 is just a simple basic AND gate, taking inputs A and B. Its result isn't the final answer, it's an intermediate output. We usually label these intermediate wires with a temporary letter, like P. Let's say A is 1 and B is 1. The AND gate processes that, and wire P becomes a 1. Great. Now we completely forget about A and B, and we look at part 2. Part 2 takes that intermediate output P, which is currently a 1, and aggressively pushes it through a NOT gate. That NOT gate flips our 1 into a 0, giving us our final output, X. By evaluating part 1 first to get P, and then feeding P into part 2, you systematically conquer the circuit. You can apply this exact chunking method to solve any circuit, no matter how massive or complex the examiner makes it.
Now for the best part, Section 5, Real-World Logic Systems. It's time to bring all this abstract theory into reality. Because while truth tables and Boolean expressions are great for getting marks on paper, these exact setups are what physically control your washing machines, the elevators you ride in, and the security systems that keep your house safe at night. Cambridge loves giving you real-world context questions, so let's practice one.
Let's tackle a high-mark real-world scenario directly inspired by the kind of questions you'll face. Imagine we are tasked with engineering a standard fire alarm that detects heat and smoke, but we want to design a logic system for a smart alarm that will bypass the local noisy siren and directly call the emergency fire service. But, and here is the massive constraint, only if the building is completely empty of people. How do we build a circuit that perfectly executes that logic without fail? I'm going to give you a mental timer here to think about what variables we need.
Time's up. Let's break it down just like we would in an exam using a structured framework. First, we clearly define our inputs. We have 3 distinct variables here. Input A is our smoke detector. Input C is our heat detector. Logically, we absolutely need both of those sensors to be on, meaning a binary 1, to firmly confirm there is an actual fire and not just a burnt piece of toast. But here is the critical catch for this specific system. Input B is a motion detector inside the building. If we want to strictly ensure the building is completely empty before calling the fire service, input B must be off. It must be a binary 0, indicating 0 motion. So, our absolute winning combination for the final alarm output to trigger is A equals 1, C equals 1, and B equals exactly 0.
And this brilliantly illustrates how we translate those English requirements into a flawless digital circuit. Look closely at how the motion detector, input B, is immediately routed through a NOT gate right at the start. That is the stroke of genius here. It means if the motion detector is off, outputting a 0 because the building is empty, the NOT gate immediately flips that 0 into a 1. That inverted 1 is then fed into an AND gate alongside the smoke detector and then into another AND gate with the heat detector. Finally, those intermediate results are funneled and combined in one last definitive AND gate. The final automated decision is made flawlessly. If there is smoke and heat and no motion, the final output becomes a 1 and the fire service is called. It is pure, life-saving logic built entirely out of the simple gates we've covered today. When you can explain a circuit like this, you are easily operating at an A-star level.
Before we wrap up, I want to drop a truly surprising, advanced fact from the world of computer science manufacturing that often appears as a tricky bonus question on papers. While we just used a combination of ands and nots to build our smart alarm, in actual physical industrial practice, computer engineers don't usually do that. They often use NAND gates to build almost everything. The NAND gate is incredibly mind-blowingly versatile. By cleverly wiring multiple NAND gates together in different configurations, you can actually perfectly replicate the function of any other single logic gate, a NOT, AND, an OR, an XOR, you name it. Because of this superpower, the NAND gate is often officially called the universal gate. Using just one type of gate makes mass manufacturing complex computer chips massively more streamlined, less prone to errors, and incredibly cost-effective. Keep the term universal gate in your back pocket for your exams.
Students who implement these computer science strategies see an average improvement of 2 grade boundaries, but only if they practice consistently with our weekly videos. As we conclude this explainer, I want you to literally look around your room right now. From the microwave in your kitchen knowing exactly when to stop, to your smart thermostat deciding when to kick on the AC, to the complex processing happening inside the very device you are watching this on. How many everyday appliances are quietly running binary 1s and 0s through these exact invisible logic circuits, making thousands of micro-decisions for you every single second? It's a hidden digital architecture that makes all of modern life possible. Here's your final reminder. Subscribe to our YouTube channel, Ace the Exams, at @AceTheExams_IGCSE to excel in your Cambridge examinations. Subscribe right now to @AceTheExams_IGCSE and click that bell. Don't let another exam pass you by without being fully prepared. Drop a comment below with your target grade for computer science and the biggest challenge you're currently facing with Paper 1 or Paper 2. Our team reads and responds to every single comment. Like and share this video with a study partner who needs to hear this. Ace the exams. Your Cambridge success starts here. See you in the next one.